I'm Amy Therian, Director of Engineering for Amazon S3, and this is my colleague, Seth Markle, who's Senior Principal Engineer with S3. I want to thank you so much for coming here today. You're here because you have a curious mind. You want to know a little bit more about S3 than maybe you can read in some documentation or watch in a video. And frankly, the S3 team is full of people like that are curious. They're so curious about how things work inside of S3 that they actually join the team as builders. So I'm hoping that today you walk out of this room with just a little bit more insight into S3. And Seth and I have been with S3 for over a decade, and our curiosity is still not satisfied. So first, I'm going to take you through a little bit of our history. So, S3, we've been serving up object storage for customers for you for more than 17 years. And over that time, we've been learning and improving our software systems to make them more resilient. If you guys are, sort of interested in machine learning at all or like analogies with machine learning, we've been training the foundational model of how to operate and build an object storage for the service for the cloud during that time. And I'm super proud of that model that we've come up with. There's really no compression algorithm for experience. So if we look back in time a little bit for S3, we went through a couple of different stages. In the early days, a lot of things sort of surprised us. We learned lessons the hard way. There were a lot of late nights, sleepless nights, reacting to things. We were very much in a reactive mode. The initial projection of usage for S3 was in the gigabytes of storage, and very quickly, more than anyone anticipated, we needed to support exabytes of storage. And so pretty soon, we wanted to kind of get ahead of problems for you, our customers, and for our builders. And so we started looking at the concept of threat modeling. Threat modeling is sort of looking ahead, looking at everything that could possibly go wrong, and trying to put in place a proactive mitigation for it. And then over time, as we learned how to do threat modeling, we instilled that as a culture within the whole S3 team, thinking about how can we constantly be proactive, looking for what those threats are, and looking for proactive mitigation. So less nights awake and more being proactive and building solutions into our service. So how does this whole threat modeling stuff work that we do? You may have heard of Amazon's doc writing culture. It is a real thing. We do write docs, and we write a lot of docs because human memory is somewhat fallible. We misremember things all the time. Our mind plays tricks on us. So if we take what's in our head, our worries about threats, and we write them down on paper, we have an opportunity in the future to reflect on that accurately and make sure that we look back and like, did we miss something? Is there something that's not quite right in our thinking? And we continue our learning process that way. Very specifically, when we do threat modeling, we create an actual document. And if we're delivering a feature, that could be one document. It could be for a very large feature, 50 documents that we write. And we have an interactive meeting where we review that document, and we review it with our most experienced engineers, like Seth here. And it's a great learning opportunity for the folks that are on our team that are newer to building resilient services. So what's in a threat model? A threat model consists of threats. And threats are things that are unexpected or could happen in the future, and they're not necessarily bad things. The word threat kind of sounds sort of negative, but they could be good. For example, having greater than expected customer usage is kind of a good threat to have. Greater than expected scale is definitely something that we love and appreciate. In addition to trying to come up with threats, we try to come up with an exhaustive list of threats. We look at what is the likelihood of that threat happening. And that's important when we're starting to develop mitigations, thinking about how good does that mitigation need to be. We have to think about how often is that threat going to happen for us in the future. Another aspect that we look at for threats is the area of impact. How impactful is that threat going to be if it does occur? Is it impacting one version of one object? Is it impacting all of the objects in a customer bucket? Is it impacting all the objects for all customers in a region? By looking at that, it sort of gives us a sense of priority of how important it is, and inspires our teams to really come up with really great mitigations for that. Now, while you're going through this threat assessment, it's really important not to get too bogged down with mitigations until you come up with that exhaustive list. You really want to do creative brainstorming. What are all those threats that are out there? Once you've got the threats, likelihood, and area of impact, then you think about what are those mitigations. And this is where things can get a little tricky. So sometimes when we're thinking about what's the proactive mitigation that we want to put in place for a threat, we introduce new threats. And so you want to keep iterating on that process until you've come up with enough mitigations and mitigations that don't introduce new threats. So what we're going to talk about today are some ways that S3 is thinking about mitigating threats inside of S3 as a service. But we're also going to talk about how you, as customers of S3, can use S3 as a mitigation for threats such as greater than expected customer usage or scale. So we're going to talk through a few of those. Now, before we get too down deep into S3, we're going to give a brief overview just to kind of give you a sense of what's going on within S3. And we've got over 350 microservices in each one of our regions. That's a lot of complexity, a lot to think about, more than we can cover in this session today. So we're going to keep it really simple with what we're focusing on today. We're focusing on the write path, so what it means to write data into S3 through a put request. So how does that work? It starts at the client. So at the client, there's some data that you want to write into S3. And at the client, our customers are using REST APIs. They might use an SDK, a CLI, or an application that can speak those REST APIs. And they start with that piece of data. That piece of data comes in as a put REST API request to our front end. Our front end is composed of DNS routers, web servers, and other components in the network. And that web server eventually interprets that put request and understands that it's a put, and it decides to put the key part of that put request into our indexing system, and then the data part goes into our storage system. Now, this is where we start to talk about some of those threats. One of the things that you can use S3 for is anticipating or leveraging, greater scale and greater than expected customer usage for your application. And to do that, you can look to our front end as the first step. Our front end is big. It is serving greater than a petabyte of data per second. That's huge. And you can leverage that scale to help anticipate and grow your applications. There's a couple of mitigations that you can use. The first is multi-part upload. The second is range gets, and the third is multi-value DNS. And we're going to talk a little bit about each one of these and how they can help you with the threat of greater than expected customer usage. So the first one is multi-part upload. So here we have a client that has 100 megabytes that they would like to upload as an object into S3. And that can be done over a single request. So that single request has some threats associated with it. Things can go wrong, like something on the internet might fail in the middle of that request. And if that happens, then that client has to restart the entire process over again, which has some slowness factors to it. It's also hitting like a single server with a single, capability of that physical web server. Alternatively, we can take that 100 megabytes and we can divide it up into chunks. So in this particular case, we're dividing it up into 20 megabyte chunks, so 5 different requests, and sending those requests in parallel to multiple servers within the S3 front end. Now, the cool thing about this is if you're dealing with one of those internet threat kind of situations or client problems or something goes wrong with the request, if it just goes wrong with one of those requests, then the application only needs to re-upload that one part. In addition to that, the cool thing is if you do this in parallel and like have them all going in parallel, you get 5x the throughput improvement. So that parallelism helps things to go faster. Each one of those requests has less work to do and they can go in parallel. And this is what it looks like in practice. Here's an example of the API create multi-part upload, and then upload each one of the parts n times. That can be done in parallel if you want to get the good throughput from it. And then when finished with all the parts, complete multi-part upload. So that's a way to kind of handle the right path. And the same is true in reverse. So we can parallelize in reverse using range gets or getting the individual parts. And again, same benefit of you may only need to re-download just the one part, or you can get that parallelization going so that you get greater or increased throughput. And here's what it looks like in practice with our CLI. So get object attributes will list all the part numbers and the sizes of each of those parts that you want to retrieve for that object. And then you can call get object to get each one of those individual parts, and then stitch that object back together so as one whole object on the client. Now, if we did all this parallelism that we're talking about, and you send it to a single server in our web server fleet, you will be limited to the capabilities of that single server. It's a real physical server, one server, one web server. It's got a certain amount of CPU, a certain amount of network capabilities. And so that's kind of limiting. Instead, you can use multi-value DNS, which will spread those requests across our entire large front-end fleet, that front-end fleet that was doing over a petabyte a second of bandwidth. And by doing that, you get to leverage all the capabilities. You can have great throughput. You can scale your application to whatever your customers need in terms of growth and even unexpected growth that you might have for your customers.
This one's actually super important. So I was working with a customer once who was having some latency issues when they were interacting with S3. And when we looked at their metrics, their traffic looked pretty smooth on like a 5-minute granularity. But when we actually went and dove into their logs, what we noticed was they were focusing that entire 5 minutes worth of traffic over an 8-second period hitting a single IP address. And so when we spread their traffic across multiple IP addresses, I don't even think we had to spread it across time, just across IP addresses, their issues went away. So this is like a very real piece of advice here that's super helpful.
That's a perfect example. Thanks, Seth. All right, so you remember a while ago while I was talking about threats and how sometimes you can introduce a mitigation for a threat that introduces new threats. Well, the thing about doing all this parallelism is that the software is a bit more complex when you talk about doing things concurrently, doing multi-part uploads concurrently or range gets concurrently. And when it's more complex, there's a risk of more software bugs being introduced. And so the mitigation that we have for that is something we call the common runtime. The common runtime is an open source library that has all the best practices of the things that I just talked about. So it's got the multi-part capabilities, the range gets, uses multi-value DNS. It has others, the best checksums, the best retry algorithms, all condensed into this common runtime. It's included with our SDK and our CLIs, so you can use it there to get all this great throughput that I've been talking about. And we're starting to include it in other applications as well. For example, we've included it in the mount point for Amazon S3 family. So earlier this year, we launched mount point for Amazon S3, which is a Fuse file connector for S3. And this month and at reInvent, we've added some features onto that. So we've added a caching capability. We've added support for containers in the form of a CSI driver, a storage interface that you can use it in Kubernetes or EKS environments. And we've added the new S3 fast storage class, S3 Express, in there as well. And this has all those best practices for best performance included from the CRT in this Fuse file system connector. If you're interested in seeing Mount Point for Amazon S3 in action, there is a session from one of our customers who used it in high performance computing. So ARM and AstraZeneca have done some really cool machine learning, a very large cluster using this Fuse connector. They were getting great performance using Mount Point. So if you're looking for a real life example, there's another session that you can take a look at there. So those are some ways that you could leverage that front end part of S3 to get really great scale, to get really great growth for your application. Next, I'm going to talk about some of the things that you can leverage within Index and also how the Index itself is mitigating some threats. So the Index is big, again, which you can use to your advantage. We're storing over 350 trillion objects in our Index, and we serve over 100 million requests per second. So it's doing a lot of work, and it's storing a lot of stuff. And you can use that a lot. We're constantly scaling the Index so that we can keep up with all of that growth of all of our customers. We want to make sure that we always have sufficient capacity because it's not great when you have not enough capacity. You can't put things in there. We're constantly keeping ahead of that for our customers. That's one of the threats that we think about is how do we keep adding and scaling out to make sure that we can handle more and more objects and more transactions per second. So this is kind of how we handle all that. Internally, we're thinking about how do we keep growing? How do we keep scaling? And so what we do is we partition all those keys over many servers. And we do that lexicographically using the letters and numbers and the key names. And this particular illustration shows what it could look like at a high level to divide them up by key name if you looked at like the first letter of the key names out there. And one of the challenges that we might see in this particular space, if you assume, for example, that all our key names are like English words, and we're looking at that first letter to figure out how to spread things out, it turns out that like in English, for example, the first letter of words is not an even distribution. It's not like A has the same distribution as Z. Vowels are super popular for starting, and there's a couple of letters, R, T, S, N, L, that are a little bit more popular at the beginning of like English words. So we might see a hotspot. So this N and S area of our partition space has two of those hot letters in it. It has N and S. And so our system will look for these hotspots and take them and spread them out over more servers. So in this case, we're splitting out N and P and Q and S to kind of spread that heat out. And that's kind of how our system works. And you can use this to your advantage as you're scaling your application, as you're anticipating your customer scale. You can use kind of a bit of understanding here to do that. Now, I'm going to explain that in a little bit of detail and how that works. But in order to do that, you have to understand what a prefix is. So a prefix in S3 is any string of characters that comes after the bucket. So anything that comes right after the bucket name that's part of the key name. And here's an example of what prefixes might look like. For a reInvent bucket, you can see that P is kind of that first letter after that. Some of these have the word, all of these have the word prefix here. Some say prefix 1, prefix 2. Prefix 1 has data and other that are part of the prefix. And we use that to kind of spread out the load across all those servers. Each prefix has 3,500 put request capability and 5,500 get request capability. And we have that so that it's easier for you to predict how can you develop the right prefix strategy to make sure that you have enough scale for your customers. What happens if you need more than that? Well, if you have just a single prefix, if you need more than that, and you exceed your prefix capability, you might get a 503. A 503 is a response that says, slow down, too much. So what do we do if we want more than what I just told you in terms of our prefix? Well, here's an example. This starts off with that 5,500 get per second, like with the bucket itself. And then we split that into two prefixes. So we have prefix 1 and prefix 2, and each one of those can get 5,500 get requests per second. And then we split that further with further prefixes. So here we add prefix 1 and prefix 2, and under those we have A and B. And that gives us a total of 22,000 transactions per second or requests per second. Pretty great. So you can use your prefix structure in order to get greater scale and greater throughput. Now, what are some things that we might think of in order to mitigate this, or things that we need to think about? There's a couple of mitigation strategies so that we can avoid getting 503s. The first mitigation strategy is keeping cardinality to the left in key names. And what that means is thinking about having as much diversity in those characters that follow the bucket name as possible. So using all the variety of characters that can possibly think of there will help improve the amount of splitting and partitioning that we can do. The second one is keep dates to the right. So dates tend to be numerical, and if you think about numbers, there's only 10 different numbers, 0 through 9, versus like the full alphabet, which has 26 and all the letters and numbers mixed together. So keeping dates to the right can help increase your capability to scale and plan for greater than expected customer usage. Now let's look at that sort of in practice. So this first example is what not to do. So don't do this. We're putting day or date to the left instead of creating diversity there, instead of putting it to the right. So we've done that, day to the left. And we split that off, and with a similar sort of TPS that we got so far, things look fine. I get 22,000 TPS from that. What happens when day 2 comes along? Well, when day 2 comes along, day 2, you start moving all of your rights to day 2. Day 1 was yesterday, day 2, I'm putting all my new data into day 2. It does not get to leverage any of that partitioning and spreading of load that happened in day 1. And so now you might see some throttles for a while as we re-spread out everything in day 2. So a better way to do this is to move all the days and the dates far to the right. So in this case, when we move from day 1 writing to day 2 writing, we get to leverage all of that load spreading that we did in day 1 for day 2, and we get to minimize any throttling. All right, so with that, I am going to turn it over to my colleague Seth, who's going to go into some threats in the storage space.
Thanks, Amy. Hey, everyone. So once again, my name is Seth Markle. I'm a senior principal engineer. I've been at S3 for just about 14 years. It'll be 14 years this February. And I'm going to be talking about how we keep your data durable and available. So a couple of stats. We have millions of hard drives that store exabytes of data. Just to give a sense of how many hard drives we have. I actually had to research this to make sure it was an honest statement. But if you stack them kind of flat way, top to bottom, you can reach this International Space Station several times over. That's how many hard drives millions of hard drives are. It's a huge number. Most people have heard of S3, have heard of this number. This is, if you don't want to count, there's 11 nines there. That's our 11 nines durability design. And we're going to talk about this number in a bit. We're going to go over specifically how this is calculated. But I want to start by highlighting that durability is much more than a single number. Right? Internally, we have a goal that we're absolutely lossless. Attendees at reInvent in 2019 might remember a talk that I did with a colleague, Andy Warfield, on S3's durability culture. We talked about several factors that influence durability. So the obvious factor that influences durability is that we store data on drives, and drives can fail. We also store drives in buildings, and buildings can have issues, right? There can be fire, there can be water. There's also issues like data can get corrupted, both on the wire, it can get corrupted at rest. We have operators running the system. There could be deployment issues, there could be bugs, there could be operator error. So if you zoom out on this, durability is actually influenced by three high-level things. So there's people, there's drives, and there's zones. So drives is obvious. Drives is the hardware that the data is stored on. Zones, or buildings or facilities you'll hear in different contexts, is actually where we're putting those drives, the physical buildings. People might be less obvious. We've actually been talking about people this whole talk. So people here refers to our builders and how our team approaches software development. So that includes things like operator errors, deployment problems, even software bugs. Those are all people-related issues. And that's where this threat modeling mechanism fits in. Okay, so with that background, let's go into this 11.9's number and talk about how we mitigate drive failure. So as usual, we start with a statement of the threat. So here, we must protect data stored on drives that can fail or corrupt bits at rest. So what are our mitigations? Well, we have three mitigations that tie together to give us this 11.9's design goal. So the first mitigation is that we start with end-to-end checksumming. This is how we make sure that what we store is actually what you gave us. When we store data, we store it redundantly across several drives, and we have background auditors that are constantly monitoring the system looking for faults so that we can react to them.
So Seth, before you move on, I want to talk a little bit about those monitors. So one of the things I'm really proud of is these monitors exist. I mentioned how stressful it can be to have the gravity of keeping care of all these exabytes of data. And it's those durability monitors, those independent monitors that make it so that I can sleep at night and know that my customer's data is safe. They're a really important part of our success in making sure that things are the right quality.
Yeah, totally. So let's talk about the first mitigation, which is end-to-end checking of requests. So when a request comes into S3, we send it through a series of services internally on our request plane. We launched a feature, I think it was about a year ago, that I believe it's called additional checksums publicly. Internally, we call it flexible checksums or flex checks, which allow customers to specify one of any number of checksum algorithms so that we can actually get checksum data from customers on the insertion path. We've had that all along, but it used to just be content MD5. And we wanted something that was more performant than just MD5. And so we've added CRC, CRC32, CRC32C, SHA-256, which isn't necessarily performant, but it's there. And so it allows us to validate checksums down our request plane. And we're transforming data as we move down this request plane. We might be framing the data as we go. Ultimately, we want to store that data redundantly across multiple drives. And so we use a technique called erasure coding. Erasure coding, super, super high level. It will divide your data into chunks. Those chunks are called shards. It creates several additional chunks, and then it spreads those chunks or shards across multiple storage devices, multiple disks. When we do that, we assign checksums to every one of those devices, every one of those chunks, rather, those shards. So in the process of doing this, we've taken data, possibly framed it, and then split it across multiple devices. So we want to make sure that we did this correctly before we go and tell you, the customer, that we've stored your data. And so what we do is we'll actually reverse that whole pipeline of transformations to make sure that the data that we're storing is actually the data that we got us. So we don't just calculate checksums as we go forward. We go backwards and make sure that we can actually rederive the data from what we had just done. And only then do we respond with a 200. So by the time you get an acknowledgement back from S3, we have not only checksummed and stored your data, but we've also reversed all of those operations to make sure that we're storing the right thing. There's a lot of checksums here. So another one of these stats I like to say is we calculate 4 billion checksums per second across the fleet. 4 billion every second. So 1 second, 2 seconds. It's a tremendous number of checksum calculations. I'm still kind of in awe of that number. So as I mentioned, we erase your code your data across multiple redundant storage devices. So here's an example. I have 5 pieces of data, A, B, C, D, and E. Each one of these kind of vertical rectangles is a storage device, and here I've spread each object across 3 devices. The fact that there's 5 and I chose 3 is just an example for illustration here. So what happens when that particular drive fails? So our background auditors will detect the failure. We're constantly monitoring the system to look for drives that failed. And when they detect failure, we're able to re-replicate that data from the other drives in the system, right? And so here we have A, B, C, D, and E. A, B, and D are able to be recovered from the other drives. And it might not be obvious from this picture, but while this is happening, those objects are still accessible from the drives that are online. So at scale, it looks a little bit like this illustration here. We have a lot of spare capacity on hand. And the way we manage spare capacity is not just a fleet of empty drives that are just waiting for their turn to join the game. We keep slack space across our entire fleet. And the reason we do that is if we lose a drive in the system, by having several other drives have enough free space to help in recovery, we're able to parallelize that recovery. Similar to how Amy talked about parallelizing multi-part uploads. And so what this gives us is a very high throughput of recovery. So when a drive fails and we detect it, we can re-replicate that data using hundreds or even thousands of drives to participate in that re-replication. Drives don't simply just fail. Drives also come with a certain bit error rate. This is the rate at which drives will just spontaneously flip bits at rest. This is just a property of storage media. And so this is where both of our techniques that we've talked about so far come in. So we have constant monitoring and we have checksumming. Remember, I'm checksumming all of the shards that go to disk. So now on a per disk basis, I can scan the shards and look for anything where the checksum, which matched at the time I put it, now doesn't match. And if I find an issue like that, I can enlist the re-replication system I just talked about to re-replicate your data. So let's piece this all together. We have data replicated across storage devices. Those devices fail at a particular rate. And at the scale of millions of drives, that rate does converge and it's measurable. We also can re-replicate at a particular speed. Right? We talked about how we use the width of the system to be able to get high throughput on re-replication. So there's well-defined mathematical models where those observed inputs, those are real-world observations that we make, get input into the model, and we come up with a durability rate. And that's what our 11.9's durability rate is. So that 11.9's is the goal, and our observations in the modeling ensure that we are exceeding that goal. Okay, so earlier I referenced the 3 kind of coarse-grained threats for durability are people, drives, and zones. And we just talked about how our 11.9's modeling covers us for drive failure. So what about availability zones? So let's read this threat. We must protect data we store against the unexpected total or partial loss of a zone. Any single facility may fail at any time, and we must protect the durability of data that's stored within it.
You know, the AZ complexity of thinking about threats is something that I got to learn a lot working with S3. I'm kind of astounded, like, how non-intuitive it can be, how much planning goes into planning for those threats. Super proud that we're able to take on all that burden of thinking about what can go wrong with an AZ so that our customers, that you guys don't have to worry about it.
Absolutely. For most storage systems, the loss of a data center is a threat that you have to think about, but our default storage classes take care of that for you. And here's how that works. Okay, so remember this picture before. This is a kind of a more expanded view of that example of 5 drives that I had before. Like I said, that was just for illustration. We don't literally do 5. We don't also literally do however many this is, 12. But this might be what a subset of our fleet looks like with blobs spread across them. And our 11.9's, again, comes from monitoring these for failure, and re-replicating them. So what we do is we take those replicas and we spread them across zones, right? And we do it in such a way that we could lose any subset, any chunk of those replicas in a zone and still be able to recreate your data if that zone is lost. And this actually happens on a request-by-request basis. So when the request comes in, it goes through that same checksum bracketing algorithm that I described earlier. Only the storage devices it uses are spread across zones, very intentionally. So by the time you get a 200 success response, your data is already able to tolerate the loss of an entire zone with no impact to the integrity of your data. Right, and so I mentioned earlier that by the time you get a 200, it's already gone through all of these reverse checksum or reverse transforms and checksumming. It's also, by that point, been spread across multiple zones. So show of hands, who heard the announcement for S3 Express on yesterday? Quite a few. Amy heard about it. So we have a new storage class, S3 Express One Zone, and this is aimed at high-performance applications. And one of the ways we achieve high performance is localizing your data in a single availability zone. So this is the trade-off that we made. So Adam talked yesterday about how our availability zones achieve isolation by actually being spread apart really far. I think the numbers he used yesterday were, I always get these reversed, but it's 60 miles, 100 kilometers. That's pretty far, and that's great for isolation, right? But the speed of light is a real thing. And the further apart you put these buildings, the higher your latency is. And so the choice that we made for S3 Express One Zone was to localize data in an availability zone to minimize latencies. But that comes with risk that customers need to be aware of. So here, a thread is full or partial loss of an availability zone may actually lose my data in S3 Express One Zone. So again, here's that picture before. This is the regional S3, all of our standard storage classes. Data is spread across the availability zones. In a one-zone storage class, those disks are in a single zone. So it's a similar replication scheme. We still go through bracketing and all that, but everything's collected in a zone. So this is how we're able to offer 11 nines of durability in a single zone. We still go through the end-to-end checksumming. We have very similar erasure coding schemes. We are auditing the data at rest using the same systems that we use for regional S3. The difference in a one-zone storage class is that it is not resilient to the loss or damage to all or part of an AZ. So this includes things like fire and water damage that could harm the AZ. And so you as a customer, when using a one-zone storage class, have to build your applications to be aware of that risk. So that typically means that you'll want to be able to put recreatable data into a storage class like S3 Express One Zone, or have a backup solution in place so that you can restore your data in case of a disaster event. The fact that it's 11 nines, though, means that in steady state, you shouldn't expect to see objects just vanishing, right? But in the unlikely case that there's a full or partial issue in the availability zone, that's when you might have to enlist a disaster recovery mechanism. Okay, so we've talked about drives, and we've talked about zones. So now let's talk about people, but from the perspective of one of your builders. This is a fictional example, but let's say in this case, your builders are building a system to clean up some of your buckets. And I talk to customers all the time where they do these one-time cleanup jobs against their bucket. So let's write out the threat here. And again, the reason we write these out is because writing solidifies your thinking. One of my favorite quotes, and I use this all the time with colleagues, it's by a cartoonist, Dick Gindin, which is, writing is nature's way of letting you know how sloppy your thinking is. I find this to be true time and time again. When you write things out, it really helps you form clarity of thought. So in this particular case, in this fictional example, we never want accidental deletion of data in Amazon S3 buckets, especially due to bulk deletion operations. So we have this threat written out, but threats need mitigations. So let's talk about what you as a customer can do if you find yourself in this scenario. So S3 offers a variety of features that can help you as a customer protect and mitigate this risk. So the first one, that's one of the more common ones that people use, is S3 versioning. So versioning allows you to preserve an object history. As you overwrite objects or delete objects, it actually creates a stack of objects for you, which on the surface sounds like, great, I can protect myself when I'm doing a cleanup job. However, if you're trying to clean up, what good is it if you're stacking the objects up because you haven't really actually cleaned up anything? And so what a lot of customers will do is they'll pair versioning with a lifecycle policy. So S3 has a lifecycle feature that does non-current version expiration. It's always a mouthful for me. So you can do something like, I'll go do my cleanup job, and I'll set a policy that'll age out the old objects after 7 days of being in that state. In the meantime, if you try to access those objects, you'll get a 404. So hopefully that gives your applications enough time to break so that your systems realize that you've done something wrong. You can stop the lifecycle policy and go figure out how to clean things up. Another feature that we offer is replication. So S3 replication copies your data between buckets. Those buckets can be cross-account, they can be cross-region, and by default, the replication takes seconds to minutes from the point where you put the object. Customers with stricter time requirements can use our replication time control feature, which has an SLA for 99.99% of objects being copied within 15 minutes. Another feature is object lock. So object lock is a feature where you can effectively lock an object and set a time when, before that time, the object cannot be deleted, no matter what, right? And so that will protect your data set. And it really is no matter what. So that will protect your data set against accidental deletion if you never want a piece of data to be deleted. Now, this is often used by customers with regulatory requirements, but it's also for customers who just need an extra layer of protection. And then backups is a general concept. So AWS offers backup solutions. We have several backup solutions from our partners. Backup systems are great, and they offer really two key features that I think are super valuable as part of the system. So one is a backup catalog. So a good backup system will allow you to be able to peruse your backup history to be able to select what point in time you want to restore from. And the other thing that backup engines offer is a restore engine. Backup without restore is not really backup. The way I've heard it described is backup is really just an implementation detail of restore. If you can't restore, why have you backed up at all, right? So restore is the most important thing, and you need to be testing your restore procedures. The worst time to test restore is when you're in a disaster recovery scenario and actually need to try it for the first time. Okay, so let's pivot to availability. So we're operating in all AWS regions. A threat that one might consider, which seems pretty easy to mitigate today, is the availability of one AWS region can never affect the availability of another region. But how many people here knew that S3 started out with the intent to become a single global service? Got a couple, okay. S3 taught AWS a lot of lessons. That's what you get to do as one of the older services. So when S3 first launched, we envisioned a single global network of storage. And so we started out with a presence on the East Coast and the West Coast of the United States. I don't actually know if I pointed east and west just now. I don't know what direction I'm facing. And so our indexing system that Amy talked about would replicate traffic between the East and the West Coast, best effort. So it would literally be a UDP packet that we sent across the country. Storage would be stored wherever the put request was received. So if I put my data into Washington, the object data would be stored there, and I'd best effort replicate the indexing entry over to Virginia. This ended up being a problem for customers for several reasons. So the first is eventual consistency. So if I'm best effort replicating my indexing, my metadata across the country, and something happens to that datagram, then it's going to take a while before I can actually see that object. If I put it in Washington, maybe I can't see it in Virginia for a while. We did have background processes that would perform reconciliation between the two sides, but those could take hours or even sometimes a day. And so you would see often high eventual consistency because of this. Also, latency is uncertain. If I put the object in Washington, but all my readers are reading it in Virginia, even though the metadata is in Virginia, I still have to haul the object bytes across the country every single time I get it. And that might be hard to predict if I don't know where my putters were. And the other issue is that the availability of an architecture like this is lower than if it were just localized in the region, because any issues with networking across the country could cause some of my data to be inaccessible. And so we don't operate this way anymore since, it says 2010 here. I think it might have actually been 2009. But S3 is a regional service. So let's revisit zone failure again, but now in the context of availability. We must remain available through the unexpected loss of an entire zone. And one of the key fundamental design goals that we have is to operate during an AZ failure without customers even realizing it. Okay, so this picture, remember this picture from earlier when we talked about how we replicate data for durability across availability zones? Well, this actually also has availability benefits. So let's say we have the temporary loss of an availability zone, for example, due to a power event. We're able to route around this failure and serve your data without you even knowing that there's an ongoing issue. And our background systems that re-replicate data in the event of a disk failure are also responsible for making sure that this property holds at all times. So we're not simply looking for free space to replicate the data. It has to be free space in a zone such that I maintain this property that any zone can get lost temporarily or permanently and the data is still accessible. This is, of course, not inclusive of the one zone storage class where the data might just be in AZ3. So as Amy showed earlier, we advertise our front-end servers in DNS. But when an AZ fails, we want to stop advertising IP addresses in the failed AZ. So we employ automation similar to ELB's zonal shift feature. I don't know if folks have heard of that. But it allows you to remove IP addresses from DNS due to some sort of signal, for example, an AZ failure. And so this automatically removes endpoints in the affected AZ, just like that. But this is why it's important as a customer to honor our DNS TTLs. Right? And you want your application to refresh from DNS frequently. The SDK does this for free for you. Right? But you want to make sure you have that IP address diversity and that you are actually leveraging the TTLs because hosts come in and out. We also run our operations considering AZ boundaries. So what does this mean? When we deploy new software, we're deploying a single zone at a time. When we adopt new hardware, we're adopting it a zone at a time. Configuration changes can occur at an AZ at a time. This minimizes the chances of an unintended bug that impacts the entire region. Why does it do that? Because we've already designed our system to be able to lose an AZ. And so by leveraging that, we're able to use that to our advantage during our typical operations and treat an issue in an AZ like an AZ loss. So we've gone through several examples of how we build our software to be correct by looking at threats and then finding appropriate mitigations for those threats. But it's also important to then go and assume incorrectness. Right? So I'm building for correctness, and we have really robust processes to make sure it's correct. But then we pessimistically want to assume it's incorrect and build our defense in depth. This is what we call guardrails. And so I want to talk about two guardrails just to illustrate some of the things that we do internally in our own operations. So the first is for our larger code changes. We will run the new and the old code paths together on the same box with the new code running in what we call shadow mode. Now, obviously, we can't do this for everything, like features that have externally visible side effects, but this technique allows us to run against billions or even sometimes trillions of requests and compare results against the previous code before enablement. And again, this is not in lieu of building correct software. By the time we get here, we're already certain that our software is correct, yet we still do this pessimistically because we assume incorrectness. Another example is that we have control plane limits. So I mentioned how we operate our system a zone at a time. For example, new hardware in a zone before we put it in other zones. In addition to doing that, our re-replication systems will make sure that even though it's still only a zone and I can lose a zone, we're going to make sure that no object is disproportionately placed on that new hardware. Right, so even though we have these controls in a zone, we have our control plane, which then goes further on a per object basis. Okay, so this is a pretty dense talk today. When we say there's no compression algorithm for experience, it's really about this focus on fundamentals that we've built from decades of experience growing and operating services like S3. The easiest thing we do is build for the happy case. Building to run in the presence of these real-world threats is much harder than the happy case, and most of our code by volume is actually for these exceptional cases. But beyond just building for these exceptional cases, what's harder still is building the organization that's designed at its core to think about these threats and mitigations so that the organization is building robust and correct hardware. And so if you take anything away from this talk, we hope is that these fundamentals take intentional effort.
Well, I just want to say thank you again for taking time to join us today. Also, thank you to Paul Megan, who is our colleague who helped us put these slides together. I have a huge ask of everyone here to please fill out the survey for this. In the suggestion text area, please let us know if there's other parts of S3 that you'd like to know. We're probably going to do another deep dive at Summits and reInvent next year, and we'd love to hear what you'd like to hear about.